Welcome to this issue of Video Vision. This time I want to talk about 5 myths or 5 erroneous statements about nuclear fusion, which you find pretty often when I do this as well. You look in the internet, nuclear fusion, you look for YouTube videos, which sometimes are loud and with music and stuff, or you look in the comments section of the videos or whatever forum where there is a discussion. And there are things which every now and then, and actually pretty often, come up, and they are usually something which are wrong and I don't like them. So I thought I'd just take 5 of them. So let's say these are 5 erroneous statements and I want to comment on them. You will see, and this is one of the things about science, there is no right or wrong in the sense that I would say, okay, this is wrong because x equals y equals z, and this shows you mathematically it's wrong. There are arguments which make you understand why the people say this, and then in the end there are arguments why I think they are wrong to the erroneous to the degree that I would not support them. Okay, so let's see. Number 1, there is the fusion constant. So fusion is always 30 years away. Whenever you look, people will say in 30 years we will have a fusion reactor, and then 30 years after it's still 30 years. Okay. Do I think so? Well, it is more difficult than people thought in the 60s when people started nuclear fusion research for peaceful purposes. They did find out in a painful process after some time that the heat insulation of the plasma is not as good as predicted by the early theories. This is because, we talked about this in other videos, there is turbulence, so there's turbulent transport which transports heat and particles out of the confined plasma. And because you have a less good heat insulation, you have to make the machine bigger and bigger. This is why the machines are not as small as the people thought in the 60s. And in fact, if you look at the ITER experiment, which is 6 meters in radius, so 12 meters the plasma torus in diameter, it's a pretty huge beast. And this takes its time in order to build it. And so this is why it's slower than predicted. Is it therefore always 30 years away? No. Because, well, if you take ITER, you could say, well, in 10 to 15 years, ITER will start the experiments in which they want to show that there is more heat produced in the plasma than is deposited within the plasma in order to heat it up, which you could define as fusion power plant or generating heat or energy from nuclear fusion. We'll talk a bit more about the generating part when we talk about myth number 4. But so it's maybe 10 to 15 years. And maybe more importantly, we used to say that, okay, we build ITER, and after we have shown that ITER works, we will build a fusion power plant. And then again, you're on this 30 years, even plus time scale. The urgency of energy problem, also the sort of positive results about nuclear fusion in the last years have actually led to quite some more money going into nuclear fusion, also industrial money, also fusion industry starting up in the world and also in Germany. And so we are now studying, can we do it faster? Can we decouple to some degree this ITER Q equals 10 success point from saying only then we will build a demonstration power or a first of a kind fusion power plant? And I think the answer is yes, we can do faster. And this is what we're studying at present. And there is one more thing about this sequential approach which people usually don't recognize. People say, this is maybe myth 1A or 1.1. People say, okay, we wait until ITER has done Q equals 10, which means the positive energy balance. Then we have learned from ITER what we want to learn from it. Well, yes and no. This is one of the purposes, but we learn from ITER, and we have learned from ITER all the time. We have learned up to now how to build these components, how to build components of the size of ITER, how to manage this in an environment where in the future, after you have done fusion, you can only go in with robots and do with robotics. All this we have learned. So it's a continuous stream of information which comes out of ITER and will come out of ITER also in the next 10 to 15 years before we even turn on the plasma somewhere towards the end of this decade. And this enables us to start designing and building a first-of-a-kind fusion power plant in parallel to the operation to ITER. So this is what is going on now. And this is also saying, well, maybe it's 20 years and not 30 years. And no, it's not 20 years now and then 20 years in 20 years. It's 20 years from when you start building it and then you have it. Okay, for this here I show you a figure which I have borrowed from the American colleagues, and it actually says in a figure now what I said in words before. On the upper half there is ITER, there is the research plan for ITER. There is the fusion power plant, FPP, but it does not come in sequence after ITER has shown Q equals 10. It actually goes in parallel, design and construction, and we learn all the time from ITER. We incorporate what we learn. These are the blue arrows which go down there. So this is the strategy which I outlined before. And now, wait, did I promise that in 20 years we will have a fusion power plant? Not really. I think what I have said is that the 30 years are not a constant. We have learned so much over the last decades that now we know more or less how to build a fusion power plant, and we could start now with the next step. We don't have to wait for ITER to do Q equals 10. We have to have ITER to learn from it all the time. But to do this, it needs significantly more finances, so there must be public and private money coming into this. And also an approach which is a bit different from what we have been doing so far, in the sense that you try things in parallel and failure is an option, and you try things such that one thing fails, you have already something else that you have developed. And then and only then it could work in 20 years from now. And even this is still a big challenge. Okay, it's a bit connected with number 2. Okay, given all this positive aspects, money which flows, more money, industry moving in, we can build a fusion power plant in 10 years. Okay, I also don't think that this is correct, because even with everything we know now, it will have to be a pretty big machine. We think we know the plasma physics. We will confirm in ITER that the plasma physics works the way we do. But even if we take this for granted, we want to build a fusion power plant. There is the technology, and one of the components, the so-called breeding blanket, in which you breed the tritium from the neutrons and lithium which is contained in the blanket, is something that is in a very early stage of development, and this will take its time. So I think 10 years is out of the question. 20 years, if we really get our act together and start speeding up, might be in reach with this. And it will be a development program of this. And because you have to design, you have to test, and then you have to build, and you can't do this in 10 years. So the 10 years I think is out of question. I don't believe anyone who says in 10 years we have a working fusion power plant. There is another aspect, which is the licensing. Such a plant will have to be licensed. There will have to be rules under which you build it, under which you operate it. These rules don't exist at present. This is not a process where tomorrow you have the rules, but you have to initiate now, and it will take years to do this as well. So there is all these things which you have to do in parallel, and you have to start now. And if you do so, I think one can do it maybe in 20 years, but 10 years is out of the question. And that actually holds for magnetic fusion, magnetically confined fusion plasmas, which are the most advanced ones, so like ITER. And everything else will take longer, because there is inertial fusion, which has had a lot of progress and positive press now. And in fact, it was a very nice result. But in terms of an integrated concept for a reactor and the technology readiness, they are not where we are in magnetic fusion. Actually, the proponents of NIF, the guys who were in this press conference and talked about the results, they said this. They said it will take several decades, maybe not 5, but several. So I think then this might be the next step, but it will not go faster. It will be slower than what magnetic fusion is doing at present. And then there are many others who claim, I know something which is wild and crazy and much better. And then I haven't seen any concept which is credible that you would think this is really bypassing any of the approaches which we have discussed just now. Number 3, we just use a different fuel and we circumvent all the challenges. Okay, yes, you can use a different fuel. Different fuel meaning, for example, different hydrogen isotopes or even proton boron 11. And yes, you would circumvent some of the problems. For example, if you used deuterium rather than deuterium-tritium, deuterium is grossly available all around the world, so there is no problem to have deuterium, whereas we've discussed a lot, tritium has to be bred within the power plant. So the breeding blanket, which I said is one of the difficult things to develop, would not have to be developed if you use deuterium as a fuel. There is even proton boron 11, which does not produce any neutrons at all, and also proton boron 11 is available. So by this you would not have to breed, and you would have only a very small amount of radioactivity. So that all sounds great. And the problem is the plasma parameters that you have to achieve in order to make these fusion reactions work are very, very challenging. So temperatures are a factor of 10 higher than what we do at present. We've discussed at length that we can just reach the DT conditions now, and in fact we need to have a larger machine like ITER in order to make this a burning plasma. And then saying, oh, I just do it a factor of 10 higher than what I haven't achieved yet is just out of order. I mean, you also have to realize this is a factor of 10 more pressure, right? So the pressure which is expanding the plasma is factor 10 higher, or the pressure by which in inertial fusion you have to compress. It's a factor of 10 higher, what we do with deuterium-tritium, where we can barely do it at present. So it's out of question. It would be great, but it's out of question. Especially for proton boron 11, you can show that if you want to do a thermonuclear burning process, it's very difficult to do because there's hardly any net energy gain from it, even if you did everything right without any efficiency losses in this. And so thermal is out of question. And there are guys who say, I have a great theory to show how it would work non-thermal. But if you look in detail at these theories, then they just sort of vanish in air because they are not really founded at present. Okay, number 4, interesting one. You're lying with your capital Q values. Okay, what is capital Q? Capital Q is the ratio between fusion power generated in the plasma from fusion reactions divided by the power you deposit in the plasma in order to heat it to the burn temperature. That's capital Q, the big Q. So are we lying about this? I don't think so. Can it be misunderstood? Yes, if you don't explain it properly. I just explained it properly, but I don't think it's absolutely clear that what it is not, it is the energy balance of the plasma, inside the plasma. I said it's energy coming out of the plasma or power coming out of the plasma versus power energy which I deposit in the plasma. It's not the overall power balance. The overall power balance of the plant is something that you could say, I take electricity from the grid in order to run my power plant, and then I generate electricity. And if you say this is Q engineering, that is the Q that people would associate with a positive net energy balance. So JET has capital U 0.7 and NIF has 1.5 and ITER will have 10. This is the plasma Q. So it means ITER produces 10 times more fusion heat than heat that is deposited in the ITER plasma. If you do the full balance, like I said, from electricity, ITER doesn't have a turbine, so it doesn't generate electricity. ITER will take probably about 300 megawatts from the grid when it runs, and ITER will generate 500 megawatts of thermal power. So if you convert this into electricity, you are left with maybe 160 megawatts, so you see it's maybe 0.5. So it is not a positive overall energy balance, but ITER was never designed to do this. ITER was designed to show the plasma energy balance. So maybe now the distinction is more clear. Are we lying about it? This is what I see in many YouTube videos. You guys are lying. Yep. No, we try to explain this as well as possible. It's not simple, as you have just seen. So we I promise to try and do even better in the future, but this is the story behind it. It is two different numbers, and it depends either if you talk about the energy balance of the plasma or the energy balance of the overall plant. Okay, number 5. Any success that you have in your research is a breakthrough. Okay, yes, there are people who do it like this. There are guys, I mean, you look at the internet, at YouTube, breakthrough in nuclear fusion, blah, blah, blah. The problem is more or less solved and so on. So this exists, but I think serious scientists, which I consider myself to be one, are a bit more careful about this. I've done this in several videos now, and I think maybe it's best to say what is a breakthrough and what is what I would call a milestone. So you have a success, and you could ask yourself, before you go to the press, you could ask yourself, is this a breakthrough or is it a milestone? So you have to think about what is the difference. So for me, a breakthrough is something that has an previously unknown or unexpected result, which when you find it, makes you change your strategy in a good way. So you didn't expect that this would be so great. It is actually great, and you didn't expect, you didn't calculate, you didn't know this, and now you know it, and now you change your strategy and say, I can build a smaller power plant, for example. That's a breakthrough. So what is a milestone? Well, a milestone is you know what you want to do, you predict that based on your calculations, you will reach a goal of XYZ. You do your experiment, and yes, you reach this. And that the result may be pretty important, but it is a planned result which confirms that you are doing the right thing and makes you go ahead with your research because you know you're on the right way. And that I would call a milestone. So this sounds a bit abstract, so let me give some examples. We made a video about 8 minutes plasma discharge in W7X. Is this a breakthrough? No, not by my definition. And I think I didn't call it like this. It is a milestone. It is something where we knew we can run the plasma for 10 seconds in this way. Very nice plasma parameters. And in principle, you should be able to run it for 8 minutes as well, but you have to change the interior of the machine. You have to actively cool it. There are lots of things where you have to be very careful if you put these large amounts of energy through the machine. We did all this. We said we want to have a milestone, which is actually 1 gigajoule of energy channeled through the machine, and that led to this 8-minute discharge. We did it. We reached it. This was a milestone ticked off. Actually, it was 1.3, so we even exceeded the milestone. It was a great result for us, a great confirmation that we are doing the right thing. It was not a breakthrough in the sense that, whoops, we didn't expect this, and now it's so great. And in fact, the Q bigger than 1 in NIF is of the same class, I would say. The guys knew very well what they would be doing. They searched for this, or say researched on this for years. They knew that if they did everything right and put these 2 megajoules of laser energy onto the small pellet, and they put this in a very spherical, symmetric way, the pellet would compress and it could go above the 2 megajoules in terms of the energy output. Mind you, this is Q within the capsule, so it is the plasma Q. I think the overall Q was about 1 over 100 or so. And they did this and they reached it, and it was a pretty important milestone because for the first time one had this number bigger than 1. But again, it was not like, okay, we do the experiment, we have a calculation, we have a expectation of what will happen, we get 10 times the energy out of it. It's not like this. It was the value that you had calculated, you do everything right. And that's, again, a milestone. It's a super important one. Again, if you look at the press conference, the guys from NIF said exactly this. So they were very honest about this. And I liked very much the way they presented. If you looked at the press afterwards, the press said, breakthrough, now we can build a fusion reactor in the next 10 years or so. No, you cannot. But you're on the right way, and you can say that my approach is working the way I expect. I can take the next step to this. Okay, so now that every success I've been talking about is all of a sudden a milestone, no longer a breakthrough. Is there a breakthrough? Well, I have an example for a breakthrough. It's a bit old one already. It's what we call H mode in magnetic confinement. This is high confinement mode. You heat your plasma. In the torus, you get for a certain heating power, because of the finite insulation, heat insulation, you get a certain stored energy. Now guys did experiment, and you would more or less know what kind of energy you get. And they started to play around with the shape of the plasma, the shape in the cross-section of the torus. And all of a sudden, for the same heating power, the stored energy goes up by a factor of 2. It was completely unexpected. Nobody had predicted this would happen. It was very positive because it said, aha, if I shape the plasma like this, I can actually be much better. If you have 2 times more stored energy, you have 4 times more diffusion power. So that's a big advantage, actually. And this I would call a breakthrough, because it is something that you find, arguably by experimenting, and you could call it luck to some degree as well. Not only luck, you actually have to realize that you're doing the right thing and that you see this. Yeah. You do this, and then afterwards you change. And the people change a lot. They change the shape of the cross-section of virtually any tokamak which had even been built like jet or would be built in the future to accommodate for this new shape which would give you the higher energy confinement. So that's what I would call a breakthrough. And yes, we have these as well, but every milestone that you tick off to go and say, now we have a great breakthrough and we will be faster, and I don't think one should do this. Okay, so that's 5 myths or 5 erroneous statements about nuclear fusion. I hope this was clarifying. If you have further questions, you can leave a comment below. But for the time being, thanks for your attention, and that's it.